Hello. Hello, am I audible? Is my screen visible? Okay, so I'll start. I welcome you all to the second live session of the NPTEL course Basic Principles and Calculations in Chemical Engineering. Myself, Chaitra Borkar, a PhD scholar from IIT Delhi, and I will be taking up this session. This course has been instructed by Professor S.K. Majumder from IIT Guwahati. Some general information about these sessions is that these sessions will be conducted every week on Tuesday from 7 to 9 p.m. And the recordings of these live sessions has been made available to you. The links has been shared with you, and you can access it through my YouTube channel as well. The session structure is that the overview of the lectures for the corresponding week will be discussed first, and then we'll solve a few sample problems. Next, now we will go through the overview of lecture 4. So, the lecture 4 dealt with the variables and properties of material in system. So process variables may be either state or thermodynamic variables, dynamic variables. So state or thermodynamic variables may be enthalpy, entropy. Dynamic variables may be either velocity, flow rate. Geometric variables may be volume or size. The examples, physical properties as variables may be viscosity or density, and for the others it can be termed as concentration. One of the examples can be concentration. So the definition of system was given. So system can be an arbitrary portion or the whole of the process unit. So suppose there is a system of adsorber plus stripper. So in that, either you can consider the adsorber as a system or the stripper as a system or the whole this unit as your system. Next, the system properties such as physical and transport properties were discussed. So physical properties can be either intensive or extensive. So intensive properties are those which does not depend on mass or size, and extensive properties depends on mass or size, and the transport properties are defined for mass, heat, and momentum transport. um, so some important properties such as concentration. So concentration can be expressed in the form of density or mass concentration, mass fraction, molar density or molar concentration, mole fraction, specific gravity, apparent specific gravity, and API gravity. So, for the multiphase systems, the volume fraction, mixture density, superficial velocity, and intrinsic velocity were discussed. Uh, for the viscosity, the different relations for viscosity of gas, dilute gas, liquids, liquid, blends, and slurry were discussed. Next, these terms such as conductivity can either be thermal, electric, or electrolytic. Diffusivity, which is diffusivity for the mass transfer. Permeability is the material's ability for it to let the fluids flow through it, and the dielectric constant. These were discussed. Next, these are some important relations which were discussed in the lecture 4. So density of a component in a mixture is for the component I. Ith component is mass of I, which is Wi, mass of ith component upon volume of the mixture. So this is the density of the ith component. Now mass fraction will be weight of the ith component. This is Wi. This is capital. So mass of the ith component upon the this will be capital W, mass of ith component upon the total mass, and it can also be expressed as the rho of or the density of the ith component upon the density of the mixture. So this is density of mixture. molar concentration or mole density is basically expressed as denoted by Ci, and it can be given by rho I, or density of the ith component upon the molecular weight of the ith component. So how this comes about to be is that molar concentration. So it it can be mole of the ith component upon the volume of the mixture. So what are the moles? So moles is weight of the ith component upon the molecular weight of the ith component. So weight of the ith component upon the volume of the mixture will gives us rho I. So rho I by mi will be molar concentration. What will be the mole fraction? So mole fraction will be the moles of the ith component upon the total moles. So or it can be Ci by C. So next, specific gravity. Specific gravity is defined as the density of the substance divided ratio of basically the density of the substance to the density of the reference. So for the reference for liquid, it is water, and for gas, it is air. And the apparent specific gravity is for those substances which have equal volume. So the weight of the substance and the weight of the reference is compared. So this is for the equal volume of substance and reference of substance and reference material. Then the API gravity. So degree API and its relation with the specific gravity is given here. So the API is basically American Petroleum Index, and it tells us if a hydrocarbon or a petroleum compound is either lighter than water or heavier than water. So if this API comes out to be greater than 10, so that material is considered as lighter than water. Next, volume fraction in multi-phase systems was discussed. So, volume fraction will be given as volume of that phase upon the total volume, or the volume of the mixture. Next, the mixture density of the multi-phase system is the relation for that is shown here. So this is the volume fraction of gas. This is the density of gas. This is volume fraction of liquid. This is density of liquid. This is volume fraction of solid, and this is the density of solid. So if there are three phases involved and we know the volume fraction and their individual densities, we can find out the density of the mixture. Next, the superficial velocity is shown here. So the superficial velocity is basically comes into the picture when there are two phases flowing in a system. Suppose there is one phase here, phase 1 and phase 2. So this may be either liquid, this may be gas, or different phases are flowing through a pipe. So suppose this is the volumetric flow rate Q, and volumetric flow rate is given, and this will be the area of the cross section. So this is A. So the superficial velocity is defined such that if there are two phases flowing in a pipe, we will consider that only one phase is covering the entire area, and it is flowing that in that way. So the velocity for that phase will come out to be Q by the whole of area. It will not flow through some area. It some area as shown here. It will as shown here. It will flow through the whole area. Okay, and the intrinsic velocity is the velocity of the particular phase flowing through their designated, I mean their actual area. So this is the actual velocity of that phase. So and it will consider the volume fraction. So as this is a volume fraction and it will always be less than 1, alpha p will always be less than 1. So 1 by alpha p will be greater than 1. So if we multiply USP both sides, so we get or the superficial velocity of a phase on the both sides. So USP. So this is equal to UIP, or the intrinsic velocity. So intrinsic velocity of a phase will always be greater than the superficial velocity for that phase. So why this is the case? Because the area for the phase to flow will be lower. So when the area is less, there will be more velocity. Okay. Next, the permeability relation is shown here. So this is the rearrangement of the Darcy law. So this is again the volumetric flow rate, and the unit will be meter cube per second. Again, this is the area, this is viscosity, this is length, and this is the pressure difference. Next, the pressure and temperature of flow process in the lecture 5 were discussed. So here, firstly, the derivation of the fluid pressure was taken up. So this is the relation for the fluid pressure. This is the external pressure, or the atmospheric or ambient pressure, which is being applied, exerted on this fluid column. And this is the pressure, and rho GH is the pressure of this liquid column itself, which has this height. So up till this height, it will be up till this height, okay? It will be P naught plus rho GH. Then the different types of pressure were discussed: absolute, gauge, atmospheric, and vacuum. So, absolute pressure is that which has the reference of the complete vacuum, or the perfect vacuum, or the zero pressure. So this will be zero pressure, and the absolute has that reference. Okay. Perfect vacuum. Now, if there is a higher level, which will be the atmospheric pressure. So atmospheric pressure is the value of atmospheric pressure is 760 mm of Hg, or it can be 1 atm. So this will be the value of atmospheric pressure. So it will be at some upper height. This is the perfect vacuum. And if the reference is atmospheric pressure, then this will be gauge pressure. Okay. So the relation comes out to be P absolute is equal to P atmosphere plus P gauge. Different measuring devices for the pressure were also talked about. However, the focus was on manometer. So manometer is a very simple device which we can construct. It is basically a U tube which has a manometric fluid which needs to be needs to have the density higher than the that of the fluid for which we are measuring the pressure. So here a system of manometer is shown here. So the external pressure P1 and P2 is being exerted on the left and the right limb of the manometer respectively, and there is some fluid in this left limb, which is fluid 1 of density rho 1, and this gray area is the manometer fluid which has density rho f, and on the right limb this density here, rho 2 of the fluid 2, and the P2 pressure is being applied. So the height of these fluid columns is also given here. So this is D1, this is D2, a height of the fluid 2 column, and this is the height of difference in the height of the manometric fluid. So this is H. So the general manometer equation is given here, and how this comes about to be is that we take this reference line. We take this. Why do we take this as a reference line? Is because we usually take the reference lines between the interface of the manometer fluid and the fluid above it, and we take it for that side which has the lower level. So this has the lower. This level is lower than this manometer fluid level. So we take this as the reference line. And we say that the pressure at this point will be equal to pressure at this point. Uh, from the hydrostatic pressure definition given here. So at this height, everywhere P will be rho GH plus P naught. So here we firstly how much pressure is being exerted on this side and how much pressure is being exerted on this side will be calculated. So firstly there is some external pressure P1 plus the pressure exerted by this liquid column. So that will be rho 1 because the density is rho 1 into g, which is the acceleration due to gravity, and d1 because that's the height of this column. On the right limb, we see the external pressure P2 plus the rho 2, the fluid 2 column, that the height is d2, g, and rho 2 is the density. And then this is the one column, and below it there is another column, which is the column of mercury. So here rho f, which is the density of mercury or manometric fluid, into g into h, which is the difference in the heights of the manometric fluid. So this is the general manometer equation given here. And if rho 1 and rho 2 is same, so this can be rearranged as the P1 minus P2. So the differential pressure here will be rho F minus rho 1. So rho 1 is the another fluid given here into GH. Next, the temperature and its scales were discussed. So it can be degree Celsius, Kelvin, degree Fahrenheit, degree Rankine. So different scales were also discussed for temperature. For lecture 6, rate of process were taken up. So firstly, the flow rate. So mass and volumetric flow rate were discussed. So firstly, I'll tell the volumetric flow rate. So if there is a pipe and there is some fluid flowing through it with a velocity, and this pipe has cross-sectional area A. So what will be the volumetric flow rate? It will be, this is the volumetric flow rate, Q dot, which will be equal to U into A. What will be the mass flow rate? Mass flow rate will be density. Density of this fluid into the volumetric flow rate. So this has meter cube per second. This has kg per meter cube. So the unit for mass flow rate comes out to be kg per second. Next, rate of momentum and momentum flux was discussed. These are the relations given here. So momentum flux. So a flux is a quantity. A flux of a quantity is defined as that quantity over the area per time. So this is the momentum flux given here. So rate of change of momentum into divided by area. So rate of change of momentum is basically the net force. And also the Newton's law of viscosity was discussed. So this is the shear stress. So suppose there is a surface, there are two surfaces, and between this a fluid is flowing, and this surface is made to move with a velocity v. Um, with a velocity v, or some force is applied here, if we can say that. So this is moving. There is some fluid between, and this is stationary. This is not moving. So there exists a velocity gradient. So this is not moving. However, this is moving. So it will take some fluid along with it, some portion of some packet of fluid along with it. But the velocity keeps on decreasing as we go down. Why does this happen? Is because of the existence of viscosity. So viscosity is an intrinsic property of a fluid which resists the flow. So because of the existence of viscosity, there exists a velocity gradient. So if this is z direction, this is y direction. So tau yz is the shear stress applied, which will be equal to the negative of mu which is the basically the proportionality constant, viscosity into the velocity gradient. Oh, sorry, dV. Sorry, dVz by dy. So next, the rate of heat transfer through the different modes such as conduction, convection, and radiation were discussed. So these are the relation given here, and this is the Fourier's law. This is the relation for Fourier's law, and this Q dot here is so will not denote as Q dot. This will be Q, and this Q dot is basically heat rate. So heat rate is given as this is the thermal conductivity. This is the area. This is the temperature difference and divided by the distance. So how the heat flows through different through between the solids maintained at different temperature. So suppose this is a solid and this wall is maintained at T1. This is this and this side of the wall is maintained at T2. So what would be the temp? How the heat and this T1 is greater than T2. So heat transfer will take place from the higher temperature to lower temperature, and this may be the temperature profile between in this wall. And what will be the heat rate is given by the Fourier law. Uh, then the heat rate for convection is shown here. So suppose there is a surface maintained at some T1 and there is a fluid flowing above it, and or it's stationary or flowing above it. So and it is maintained at T2, and suppose T1 is greater than T2. So what will be the rate of heat transfer from this solid to this fluid or this surface to this fluid? So it is given by this uh, uh, convection heat rate. So this is the heat transfer coefficient. Mind you, this is the surface area. So the area between the heat transfer here is surface area, while area between the heat transfer here is the cross sectional area, because this will be a 3D object. So the cross sectional area will be the area considered here, VS area, and the temperature difference between the surface and the fluid. Next, the radiation heat rate are shown here. So this is for a perfect black body which absorbs all the radiation irradiate on it. So this is the Stephen Boltzmann constant. This is again the surface area and the temperature raised to power 4. For the gray bodies, the relation is given here. So there will be some portion of it will be absorbed and some portion will not be absorbed. It may be transmitted or reflected back. So this factor takes care of that. And again, this multiplied with the radiation for the black bodies. Then the radiation loss is shown here. If there is some radiation loss from hot to the colder body, so the relation for that is given here. Next, the rate of diffusion. So diffusion rate is given by the Fick's law, as shown here. This is the mass flux. Mass flux, which is equated to the negative of diffusivity by the concentration gradient. And the rate of mass transfer. Now this is again the mass flux, but this considers both the convective, sorry, the advective. This may consider both the advective and the diffusive one. So this is the mass transfer coefficient here, and this may be the concentration at the surface or the interface, and this may be the concentration in the bulk. So this accounts for that. And the rate of reaction for A giving B, the rate will be equal to the disappearance of A. So the change in the concentration of A upon the change in time. And then the rate law and the order of reaction were discussed. So we'll start with these first. We'll start with these some sample problems now. So first question is dash is an extensive property. So what will be the correct answer here? What will be the correct answer here? Can anybody tell me? It's given, I just showed you. So let's discuss. For extensive property depends on the size or the mass. So temperature will not depend on the mass. Moles will depend. Pressure will also not depend. And concentration will also not depend. So why does concentration does not depend is basically if you have a solution, 1 liter solution, which has some concentration, suppose 0.1 mole. If you remove some volume of it, so suppose you take 0.5 liter now, but the concentration will still remain 0.1 mole, 0.1 molar. It will not change. So the concentration is also not an extensive property, it is an intensive property. And another rule here is that if you divide two extensive properties, it becomes an intensive property. So this logic can also be applied here. So concentration can be moles per volume or mass per volume. So mole is an extensive property, volume is also an extensive property. So division of these two will give us an intensive property. So concentration is also an intensive property. So the correct answer here is moles. Which of the following is not an example of transport property? So as we have seen, viscosity takes takes part in momentum transfer. So this is this momentum transfer. Diffusivity takes part in mass transfer. Conductivity takes part in heat transfer. So these are transport properties because they express either mass, momentum, or heat transfer in some way. However, the specific gravity does not do such thing. So it is basically the ratio of some substance upon the reference. So the correct answer here is the C option. A solution of specific gravity 0.8 consists of 40% A by weight and the remaining B. If the specific gravity of A is 0.61 and if volumes are additive, the specific gravity of B is. So what is known here is we have some solution of specific gravity. So we'll write what is given here. So rho solution or the specific, sorry, firstly the specific gravity of solution is given. Specific gravity of solution will be 0.8. So specific gravity will be rho solution by rho water. So rho water is 1 gram per cc if we take that. So 0.8 by 1. So rho solution comes out to be 0.8 gram per cc or cubic centimeter. So this is the rho of solution we know. And if we and what is the Mass fraction of A, so WA is 0.4. So WB will be 1 minus 0.4, so 0.6. The specific gravity of A is given 0.61. So again, the rho of A will be from the same logic, will be 0.61 gram per cc. We don't know. What we need to find out is Sg of B or rho of B basically. So we don't know that. So rho of solution can be found out uh, by weight of solution by volume of solution. So if we take basis as 1 gram of solution, so weight of solution will be 1 gram. We don't know what is the volume of the solution. So this can be found out using rho of solution. We know the rho of solution. So volume of solution will be 1 by 0.8. If we rearrange this, this goes up and this goes down. So 1 by 0.8, 1.25 cc. So this is the volume of the solution. Now we will equate and volumes are additive. So V solution will be is equal to VA plus VB. So we can find out VA because we know what is the weight and the density of A. So that will be equal to WA, capital WA by VA. And this will be WB, capital WB by VB. So, sorry, rho A. My bad. This will be rho. Yeah, this will be rho. So, this is 0.4 because if 1 gram is taken and this is the mass fraction, so WA will be 0.4 gram and WB will be 0.6 gram. So 0.4 by rho A. Rho A will be again 0.61 plus 0.6 by X because we don't know this density of B. So volume of solution again is 1.25. If we solve this, this comes out to be 0.655 plus 0.6 by X and 1.25. So 0.6 by 0.595. If we subtract 0.655 from 1.25, this comes out to be 0.595 and 0.6 by 0.595 is equal to X. So this comes out to be approximately 1.01. This is the density of B, gram per cc. And if we apply the same logic as this, so density of uh, rho B is equal to X is equal to 1.01 gram per cc, or SGB will be the same as 1.01. So the correct answer here is the first option A. Next question. Which of the following is not correct? 1 atm is equal to, so here we see, we know that 1 atm is equal to 1.013 bar. or 101325 Pascal or 101.3 kilopascal. So these are correct options. However, this is 1 atm is equal to 760 mm of Hg. So mm of Hg or mm or head of some fluid is another way of expressing pressure. So we know P of some fluid can be equal to rho gh. So this this h can be Pf by rho g. This is another way to express. So this is called head, pressure head. This is another way to express pressure of a fluid. So this is 760 mm of Hg, 1 atm, 1 atmospheric pressure, not 740. So this is the correct answer. Match the following. So as we have discussed, we need to find out what is the correct option for gauge pressure. So from here we can see that P atmospheric is the reference for gauge pressure as we have discussed. Then for absolute pressure, perfect vacuum as the reference. Then for STP, this is not the correct answer, question here. This will be NTP, sorry. And for STP, it will be 273.15 Kelvin and 1 bar. So the standard temperature and pressure conditions are the 273.15 Kelvin or 0 degrees Celsius and 1 bar. And for normal temperature and pressure, it is 20 degrees Celsius or 292.15 Kelvin and 1 atmosphere. So atmosphere. So the correct option for this will be 1. So the correct answer here will be A4, B3, C2 and D1. So C option. Next question. Unit of heat flux is, so from the Fourier law, we note that this is heat rate Ka delta T by L. So this is heat rate. Now I have told you that flux of a quantity is that quantity upon area into time. So flow of a quantity per area gives us flux. So if we take this area on the right side, so Q by A, which will be Q, that will be minus K delta T by L. So this is another expression for Fourier law. So this equates heat flux to the product of thermal conductivity into the temperature gradient. So from here we can find out what will be the unit. So from here we can find out what will be the unit. So heat rate is uh, so heat is basically energy. So joule per second upon area. So area is meter square and joule per second is watt. So watt per meter square. The correct answer is watt per meter square. Choose the correct relation for intrinsic and superficial velocity. So as we have discussed already, so intrinsic velocity is for a phase is superficial velocity of the phase upon the volume fraction. So as this volume fraction is always less than 1, so this whole relation will always be greater than USP. So UIP is greater than USP. Another logic, as I have said, is that if we consider only that area through which the fluid is flowing in one phase, so that area will be lesser than this whole area. So if the area reduces, the velocity will be faster than the superficial velocity at least. So this is the correct answer here. The dimension of dynamic viscosity is, so dynamic viscosity is the viscosity that we have been discussing up till now. So if we see tau by z minus mu dvz by dy. So this is shear stress. This is the velocity gradient. Now shear stress has similar connotation as pressure, and the dimension and the unit of shear stress is same as pressure. So the dimension here or the units of shear stress will be Pascal. The unit here will be meter per second, and this will be meter. So if meter get cancelled, and this will be per second if it goes on this side. So minus mu Pascal second firstly is the unit, and what will be the dimension of dynamic viscosity will be, so this is Pascal. So Pascal is Newton per meter square into second. So Newton is kg meter per second square upon meter square into second. So divided get cancelled, one s get cancelled. So kg per meter per second. So dimensions of dynamic viscosity will be ml minus 1 T minus 1, because this is m L minus 1 T minus 1 kg per meter per second. Next question. An oil of specific gravity 1 is flowing through a pipe. A differential manometer is connected at the 2 points, say A and B, and shows the difference in the mercury level as 20 centimeter. What will be the difference between the pressures at the 2 points? Take rho Hg as 13,600 kg per meter cube and G as 10 meter per second square. So there is this pipe and the fluid is flowing through it, and the manometer is connected at the 2 points. So there is some pressure P1 at this point and pressure P2 at this point. So and there is some fluid here. That oil fluid is here and some fluid is here as well. So there is a pressure difference between the 2 points, and this is the difference in the heights of the manometric fluid. So this we will term it as H. This we will term it as this height of column. This column of fluid. This height will be D2. This will be D1. So from here we can say that D1 is equal to D2 plus H. So this H is 20 centimeter or 0.2 meter. If we convert everything in SI units, keep the unit consistent. So from this manometric equation, we can write this as, so we need to find out P1 minus P2. So P1 plus rho 0. So rho 0 again, the specific gravity uh, uh, sorry. So rho 0 will be specific gravity of oil into rho of water. So rho of water is again 1000 kg per meter cube, and specific gravity is 1, so 1000 kg per meter cube. So we need to keep use the SI units only. So the density of water will be 1000 kg per meter cube, and rho of oil will be 1000 kg per meter cube. Now, so from here, we can put the values in this relation. P1 into 1000 into G, which will take as 10, and D1. D1 is given here as D2 plus H. So D2 plus 0.2. Then it is equal to P2 plus again 1000 into 10 into D2. So this is this column. We are considering this column. This is the value for this column plus the manometric fluid. So 13,600 into 10 into H. So H again is 0.2. So here we can see that this and this point gets cancelled. Only this 1000 into 10 into 2.2 will remain. So this will come this side and P2 goes to that side. P1 minus P2, 13,600 into 10 into 0.2 minus 1000 into 10 into 0.2. So if we take 10.2 and 10 into 0.2 common, so 2 into 12,600, because this is negative sign. So 13,600 minus 1000 is 12,600. So this will come out to be 12, oh sorry, 25,200 Pascal. So this is the pressure difference, or 25.2 kilopascal. So the correct answer is A part. The right limb of a simple U-tube manometer containing mercury is open to the atmosphere, while the left limb is connected to a pipe in which a fluid of specific gravity 0.8 is flowing. Now, the center of the pipe is 12 centimeter above the level of mercury in the left limb. Find the gauge pressure in the pipe if the difference of mercury level in the two limbs is 20 centimeter. The difference of mercury level in two limbs is 20 centimeter. So this H2 is 20 centimeter or 0.2 meters. Now it is given that the center of the pipe is 12 centimeter above the level of mercury in the left limb. Center of the pipe is 12 centimeter above. So this H1 is 12 centimeter or 0.12 meter. Now we need to find the gauge pressure. So there will be some pressure exerted here. So P, and we will use the manometer equation, and this will be the reference line again. So P plus rho of fluid into G into H1 is equal to P atmosphere, because this is open to atmosphere, plus rho of mercury, rho of mercury into G into H2. So we need to find out the gauge pressure. So that will be equal to P minus P ATM because this is open to atmosphere. So P minus P ATM will give us the gauge pressure and rho mgh2 minus rho fgh1. So if we put in the values here, so 13,600 into 9.81, as it's not given here to take acceleration due to gravity as 10 meter per second square, so it will be 9.81. H2 will be again zero point 0.2 minus, so here again the specific gravity is given to us. So specific gravity or this rho of fluid will be specific gravity of fluid into rho of water. So again 0.8 into 1000 kg per meter cube. So it comes out to be 800 kg per meter cube. So again, so this will be 800 into 9.81 into 0.12. So P1 minus P2 will be, so if we compute these values, 13,600 into 9.81 into 0.2, it will be 26683.2 subtracting 800 into 9.81 into 0.12, which will be 941.76. So this comes out to be 25741.44 Pascal or 25.74 kilopascal. So the correct answer here is approximately the first option. So SI unit of viscosity is, again we have discussed this before. So shear stress upon the velocity gradient. So again, this has unit as Pascal. This has unit as meter per second upon meter. So meter get cancelled, per second goes up. So it comes out to be Pascal second. So the correct option here is B. This is incorrect. This will not be the answer. It will be Pascal second. Next question, match the following. So we need to match the relations for the different temperature scales. So first we'll go for the degree Celsius temperature scale. So what will be the correct answer here? So the correct answer, as we know, that if we need a temperature in Kelvin, so we require from degree Celsius temperature, we need to add 273.15. So if we want a degree Celsius temperature, we need to subtract, and you have a temperature in Kelvin, so we need to subtract 273.15. So A connects to 2 in the second column. The relation for degree Fahrenheit, what will be the correct answer here is, if we look at the fourth option, this is the correct answer here because the relation between degree Fahrenheit and degree Celsius is uh, into 9 by 5 or 1.8 plus 32. So B connects to 4. Rankine is another temperature scale, and its relation with Kelvin is, if we multiply the Kelvin temperature with 1.8, the Rankine, we get the Rankine temperature. And for Kelvin, now this is the last option, so it connects to 3. And the conversion from Fahrenheit to Kelvin is shown here. So if we have a temperature in Fahrenheit, if we subtract 32 and divide by 1.8 and add 272.15, so we'll get the temperature in Kelvin. So the correct answer here will be A2, B4, C1 and D3. So the last option here is the correct answer, D. Next question, shear stress as the dimension. Uh, Again, we have discussed this, the shear stress as the dimension the same as pressure. So pressure is force per area, and force is mass into acceleration per area. So kg into meter per second square upon meter square. So the units is of the pressure is this, or tau. So it is kg per meter second square. So the dimension will be m L minus 1 T minus 2. So the third option here. Next question, question 14. Heat is transferred from a wall having a thickness 5 millimeter conduction only. One side of the wall is maintained at a constant temperature of 100 degrees Celsius and another side is maintained at 50 degrees Celsius. The thermal conductivity of the wall is 0.8 watt per meter Kelvin. Just a minute. Yeah. 0.8 watt per meter Kelvin. Calculate the heat flux kilowatt per meter square through the wall and conduction only. So the conduction, only the conduction mode is being considered here. So suppose this is a wall of thickness 5 mm and suppose, and this is this side of the wall is maintained at T1 temperature, which is 100 degrees Celsius, and this is at T2, which is 50 degrees Celsius. So there will be some temperature gradient as the heat is transferred from this side to this side, because heat transfers from the higher temperature to lower temperature. And the thermal conductivity, which has the unit watt per meter Kelvin, so SI unit again, is given to us 0.8 watt per meter Kelvin. And we need to find out the heat flux. So I had told you that Q, or Q dot by A, is equal to minus K delta T by L. So we know the L, 5 mm, or we'll convert it to SI unit, will be 0.005 meter. So we can find out the heat flux. So we know the thermal conductivity, 0.8 into the final temperature is 50 minus the initial temperature 100 upon L. So this is 0.005. So 0.8 into 50 by 0.005 again. So it comes out to be, Q comes out to be 8,000 watt per meter square, or 8 kilowatt per meter square. So the correct answer here is 8 kilowatt per meter square. Next question, for convective heat transfer, surface area is considered. So what will be the correct answer here? Is it true or false? So the correct answer here is true. as we have seen that Q convective HAS TS minus TS. So as there is a surface and a fluid is above it, surface, fluid. So the heat transfer from the surface to the fluid, and this area here will be the surface area. Considered will be the surface area. So the area between these two interfaces, area of the interface is the surface area basically. So surface area will be considered. So this is true. Next question, this is an easy one. What would be the correct option for reaction A giving B? So for a reaction A giving B, with time the concentration of A will decrease because it is A is forming into B. So and B from 0 it will increase. So A will be the second profile and B will be the first profile. So the correct option is B. Next question, the order of the reaction of the for the rate law. So we are given the rate law as, so we need to add the power of the concentration or the reactant. So A power of A is 1 and power of B is 0.5. So the order comes out to be 1.5. Next question, the unit of rate constant for zero order reaction is. So we know for zero order reaction R is equal to K. For first order reaction R is equal to KCA. So unit of rate is change in concentration per time. So mole per liter into time or second. So it will be then the unit of rate constant for zero order reaction, which is this rate, will be the same. So the unit of rate constant for zero order reaction will be the same as the unit of rate. So mole per liter per second. So this option. Next question. The SI unit of permeability is. So we had seen the expression earlier for the Darcy law, the relation. So Q is equal to minus K so we need to find out the unit, SI unit of permeability. So unit of Q is meter cube per second. And if we take all this on this side, so area is meter square. This is again kg per meter second square. And this again is kg per meter per second into meter. So this per meter and per meter gets cancelled. This is per second square and this per second square gets cancelled. What are we left with is this meter and this 1 meter gets cancelled and this another will be get cancelled. So we get meter square. So the unit of permeability is meter square. SI unit. Last question. What is the relation between absolute pressure and gauge pressure? So P abs and P gauge. So what is the relation between that is, as we have seen, the absolute has zero or the perfect vacuum as reference, and the gauge has the atmospheric pressure as the reference. So the absolute pressure will be the sum of gauge pressure and the atmospheric pressure. So the correct answer here is option B. I hope there are not any questions. So I will go ahead and close this session for today. If there are any questions, you can let me know. If there are any questions, you can let me know. If there are no questions, I'll go ahead and close this session for today. Thank you so much for joining.